Bret Butler is going to get set up with his PA. He has a presentation. How does wind impact firefighter safety zones and size? So when he gets ready, we'll let him take the mic.
This one at that room will be till 16:20.
Okay.
Okay.
Yep.
Any case, we are.
Okay, very good. Yep. And if you want an update. Okay, great. Okay.
Today I'll talk about wildland fire and how wind affects firefighter safety zones. I'm happy to be here today. It's a fantastic country to visit. My wife and son came with me, and it's been really enjoyable the week that we've spent here so far. In 1957, there was a fire in Southern California called the Inaha Fire, and a crew working on that fire was entrapped, and 11 members of that crew were killed. In the aftermath of that fire, there was, of course, an official investigation and a study of what happened and why that entrapment occurred. And one of the phrases or terms that came out of that official study was the term safety zone. That's the first place I could find it in any of the official literature, the term safety zone. What does a safety zone mean? The official definition is this: a pre-planned area of sufficient size and suitable location that is expected to prevent injury to fire personnel from known hazards using fire shelters. The term safety zone, it also led, or this study also led to the development of standard work guidelines, 10 standard fire orders, and 18 watch-out situations that all wildland firefighters in the United States were expected to follow. One of those orders was that every wildland fire should identify a safety zone whenever they're working on a fire. Now, that was in about 1960. When I studied the South Canyon fire in 1994, there was a lot of talk about safety zones. What were safety zones? Where did those firefighters go that were working on that fire? And I asked myself, I was fairly new in the Forest Service and had come from a non-fire background, how do you define a safety zone? When do you know if you have an adequate safety zone? What attributes constitute an adequate safety zone? I've spent much of my career asking and trying to answer that question. There have been three theoretical studies, trying to determine or define what a safety zone is. This work that myself and Jack Cohen did in the late 90s produced this line. So we define safety zone as the minimum distance to burn injury. So you could call it the radius of a circle if you have a circular safety zone. And the way we present our results is that distance divided by flame height as a function of flame height. And out of that work that we did, we developed a guideline, a rule of thumb for all wildland firefighters, that they needed to have an area that provided a safe distance equal to 4 times the flame height. And that was simply by fitting a line to this curved line, a straight line. There have been since 2 other studies, one by Rossi et al. In 2008 and another by Zarate et al. In 2011, That's essentially these two lines. Similar approach, primarily simulating the fire as a radiant panel, a steel sheet, if you will, of high temperature, emitting radiant energy to the surroundings and defining the distance at which you would receive second-degree burn injury. Now, there's some problems. First of all, in this area right here, I've always asked and have been asked why this occurs. It doesn't really make sense for these small flames, if you will, short flames, less than 3 meters. Does it really make sense that we need to be that far away from the flames? In some work I did in 2014, I postulated, theorized, that these points were inaccurate, that actually these lines should not exceed 5 or 6. Well, this recent work that I'm going to present today, we'll take a look at that. So I'm going to talk about three experiments. 2 of them are on it's a propane burner. It's about 4 meters wide, and it's built to simulate fire impacts on wildland firefighting vehicles. The first series of experiments we did, we ignited the burners, and then I measured the radiant energy as a distribution, as a function of distance from those flames. And what I'm pointing out here is for low winds, this flame, you have a symmetric profile of radiant energy, if you will, as a function of distance from the flame. The next series of experiments that we did, we had just by happenstance, we had a wind of 2 to 3 meters per second blowing on the flame. And when I was trying to think about what I could talk about that would get me authorization to come to Spain, I thought, well, maybe this would make a good story. And it did, at least to the organizers of the meeting. So what I found, I think this is really interesting. I found that on the downwind side, where the wind's blowing, there's a substantial change in that radiant profile, in that heating. Not radiant, this is total. This is convective and radiant heating. You have to be farther away from the flame for a given energy level. So if we were to say that this level was the burn injury level at which you received second-degree burn injury in 20 or 30 seconds, when a low wind, a 2 to 3 mile an hour, meter per second wind is blowing, that distance almost doubles. If we look at higher wind speeds, this is another set of experiments. These were pine needle beds that were 3 meters wide by 24 meters long, burned in a facility that had the capability to go to exceed 100 miles an hour. Of course, the highest speed we tested was 20 meters per second. All right? And we measured a substantial change in that energy distribution as a function of distance from the flame on the downwind side with increasing wind speed. So I just have to add a little quick story. When I checked in the hotel the other night, my briefcase disappeared. I did have slides with data points on them, so I didn't make up this data. There are data somewhere on the streets of Barcelona. And I wonder what somebody is doing when they're looking at those slides. These are my recollection of what the data look like. This is probably smoother lines than what they really look like. Anyway, at low wind speeds, what you see, what I interpret is 2 meters a second or lower. You still have an increase, if you will, in heat flux as you get closer to the flames. That makes sense. At a wind speed of 10 meters a second, Again, the same thing, but you have to be farther away to reach this burn injury limit. And the same thing at 20 meters a second. So does this still problem? How does this address this problem that I talked about at the beginning? This is what I interpreted before to be an overestimation of the distance that you need to be away from the flames to prevent burn injury. If I plot those data from the previous graph on this graph, this is about where they fall. So I find it really kind of fascinating. What it says to me is that as the wind blows stronger on the flames, you get longer flames. That makes sense, right? And they radiate and emit more energy. And that is shown here. As flame heights don't change, but the distances that you need to be away from those flames as a function of wind speed increase. So we don't plot wind speed on here. These data segregate out by low wind speed. If I back up here, these low wind speed data are at the lower part of that curve. And similarly, so we have the low wind speeds here, moderate wind speeds, and the high wind speeds plot out up here. So the take-home messages are maybe, and this is pretty apparent probably to those of you who spend a lot of time in fire, but it's nice, I always think it's nice to have some data to back up your observations. For low wind speeds, below a meter a second, and flame heights from up to about 4 meters, there's no change in the distances you need in terms of safety zone size for what you would have for no wind at all. But if you get even a slight wind, 2 to 3 meters per second, and I found this surprising, it was only that much wind. It took very little wind to cause a substantial change in that safe separation, this SSD, safe separation distance, or the ratio of separation distance over flame height. And for very strong winds, you have a substantially, even more greater increase in that safe separation distance. So this may have, and does have, implications to all of us who work in wildland fire. If we're in an area where there's a potential exposure to wind, we need to consider that wind in the context of our separation distances and our safety zone size. Again, it's not a new finding. We all recognize this, but I think this gives us a little bit of quantitative numbers to go with our observations we've made in the past. Finally, I'm happy to be here. And if you have any questions, I would love to receive emails. Send me an email, and I'm happy to respond. Thank you.
Thank you for your presentation, Bret. I think that I probably echo many people's feelings in this room that we'll look forward to your next presentation to include this data with topography, because you add wind onto our safe zones and then put us on the side of a slope. And we really do have hazards that should concern us all in operations. So thank you for that. Any questions for Bret? Does anyone want to raise their hand that has his computer? Because he'd really like it back. Just kidding. Any questions? Sure.
Bret, may I ask if you want to go back to one of your slides?
You're trying to find some data, aren't you? It's not there, Domingos.
That one can be that one. I don't understand this graph. That headline says that it is 4 times the flame height. But the flame height is increasing, so that should be a line also increasing, no?
Well, it's divided. It's the separation distance decreases with flame height also, so they counteract each other. Does that make sense? So separation distance, flame height is, I don't know, maybe you're right. Domingos. I've plotted it before like this. I mean, the idea is that it's a linear fit to this curved equation.
Okay, there's something I don't understand. Okay, thank you.
Yes.
I have to pass the microphone so we get it translated. Excuse me. There you are.
Thank you, Bret. Would it be more accurate if you used flame length as opposed to flame height?
I'm sorry, what's that?
Would it be more accurate if you used flame length as opposed to flame height?
Yes, that's a great question. Fantastic question. And I feel like, this is my personal opinion, that from my interpretation of these results, I say that they're the same. Flame height and flame length are the same. I know that's not the case, but I want to be conservative in my estimates, and flame length is going to be greater. So by using flame height, you're more conservative in your estimates. So either way, I think it's fine either way. I think it's easier as humans when we're viewing flames. When we see a flame, we typically do not see flame length. We see flame height. We're either seeing, we're not looking at a nice side view of the flames. We're seeing something we're measuring from the ground up rather than the length of the flames. So that's primarily the reason I use flame height. But you're right, flame length would probably be a more accurate representation. It's just, I think that's more difficult as a firefighter to estimate. And overall, I think that this issue with flame height is a major problem, because this requires that firefighters and fire managers estimate the fire ahead of time. If you say you have a crew going out on a fire, you need to have a safety zone this size, then you have to estimate what the flames, either height or length, are ahead of time. That introduces too many uncertainties in the process. So the new direction that we're heading, and there was a hint of this in the talk that Joaquin Ramirez gave this morning. We're developing a digital device app that does a calculation, and that calculation, it's a proposed rule for safety zone size, is not based on flame information, but on vegetation. Or maybe something else, but right now we're using vegetation. But I would like to get away from the flame, whatever it's flame height or flame length, either one, because you have to estimate those ahead of time.
Thank you.
Did you have a question?
Yeah. Hi, sorry. Just leading on from the last question, in terms of flames, I spent a lot of time looking at forest fires and different fires, but very little time studying actual flames. I'm just curious where the heat in a flame is generated, which part of the flame is generating the most heat and radiating that in different transfer mechanisms. Thanks.
Radiant energy is proportional to the temperature of whatever is radiating, in this case the flames, raised to the fourth power, the power of 4. Right, so a typical temperature profile in a flame is about, 600 degrees centigrade at the tip, at the top of the flame, and the peak of the, say, to 1,000 or 1,100 degrees centigrade at the lower third of the flame. Right, so the bulk of the energy, actually probably 80% or more, comes from the lower 2/3 of what we see visually in the flame. So I think we're often also, when we try to visualize flames, we overestimate the heights, because it's really impressive visually to see those big globs, if you will, or clouds of burning gases that move up above flames. They really don't generate much energy in terms of what the impact on humans or plants. The bulk of the energy comes from the lower 2/3 of the flame for those reasons.
Thank you, Bret. I think this is great fire information for all of us. And one of the things this conference does is build out time for you all to be able to seek our speakers out. Please take no offense at my joke about the computer. That was a bad joke. What is good news is it was a government computer, so all this data is locked up, and no one else is going to get it. Yay. All right, you're welcome to switch out if you'd like to, and we'll have our next speaker. Thank you.